So if we focus only on two convolutions, meaning two layers, meaning this convolution right here and this convolution right here, so we'll have this input tensor, we perform this convolution, and then we feed into this first convolution of the bottleneck. See that both of them have 1x1 convolutions. So if we focus on only those two, and we run this, we have layer 1 and layer 2. So layer 1 has this input shape and these weights. Remember that the input shape is the batch, channels, height and width, batch, channels, height and width, and the shape of the weights are output channels, input channels, and then the kernel size, 1x1. Output channels, input channels, and then the kernel size. And this plane 16 by 16, but think about it as 160 by 160. So if we have 160 by 160 by 128, if we perform the convolution with the weights of that layer, meaning we need 64 in the output dimension, and we have 128 on the input dimension, if we perform this 1x1 convolution, you can see that it is kind of like a network in network, in the sense that for this 1x1 and 128, we're going to perform the dot product with the weights, and the result is going to be a single number. Here it says it maps an input pixel with all of its channels. Think about this top left corner, this input pixel with all of its channels, in this case 128, it maps that to an output pixel, maps that to an output pixel, this 1x1 pixel, and it can be squeezed to a desired output depth, which in our case, that depth is 64. So we have mapped this 1x1 by 128 to 1x1, and we've been able to achieve that because the tensor values of this 1x1 by 128 tensor has been convoluted with a 1x1 and 128 of weights, where every value of the input tensor has been multiplied by the corresponding weight, and those 128 operations plus the bias and the activation gives you a single value. And then similarly, this tensor right here, we have 160 by 160 by 64. But if we focus on this one pixel right here, this 1x1 by 64 will be convoluted by the weights of that layer, 1x1 by 64, to give you a single value. So you're mapping the input pixel and associated channels to an output pixel, and you can determine the depth, which in this case, 64. So you have 64 combinations of 1x1 by 128 weights. And then in this case, layer 2 of this tensor convoluted with the weights will give you a tensor of the same size, 160 by 160 by 64. And this same representation that you see here, we can see it in a different way as well, where we have, again, layer 1 and layer 2, layer 1 and layer 2. And this is what's coming to this layer. And then you can see that these 128, they get mapped to a single value. You have this 128, these are the number of inputs and also neurons that you have. So layer 0 coming to layer 1 has 128 neurons, each corresponding for a channel. So these 128 values will all map into a single value. This one right here, for example. All these 128 map to a single value. And then you have 64 of those. So you can see that layer 1 has 64 output channels, which also correspond to 64 neurons. And to show how dimensions match, we have the weights of layer 1, the output, and then the input. So 64 by 128. And then to that matrix weight, you perform the dot product with the input. In this case, the input has dimensions 128 by 1, 128 by 1, that single pixel, that single input. And then the dot product of this operation will give you a tensor of 64 by 1. You'll add the bias term, which has the same dimension, 64 by 1, because every neuron has a bias associated with it, and we have 64 of those neurons. You perform the activation, in our case, the silo activation, and then you obtain the output, x1, which has shape 64 by 1. So when you feed forward that to layer 2, meaning this one right here, layer 2, then your output of layer 1 becomes the input to layer 2. And now we have a weight matrix for this layer of 64 by 64, because both the output channels and the input channels have the same dimensions. So we performed that product of that weight matrix with the input, which we calculated is 64 by 1, and that gives us a 64 by 1 as well. Remember, with that product, this one and this one go away. So we have this 64 and 1. And then we add the bias terms for every neuron to obtain, again, 64 by 1. So 128 by 1 became 64 by 1, and then that one also became 64 by 1. Our 128 by 1 became 64 by 1, and that one also became 64 by 1. And that's how we can map channels within 1 pixel to the next layer. So this is one of the advantages of using 1x1 convolutions, which is feature mixing, that allows us to mix information across channels without affecting the spatial dimensions. You can also perform channel reduction. In this case, we went from 128 to 64 channels, and you could have reduced it even more. But in this case, we used 64 so that later we could concatenate them into 128 again. We also introduced nonlinearities. In our case, we performed the silo activation. And these nonlinear transformations allows us to learn different patterns, more complex representations. We've seen that these 1x1 convolutions, combined with the bottleneck layers, allow for better computation without sacrificing performance. And since we're using these parameters, this helps in generalizing the model and avoid the risk of overfitting.